My friends, let us talk about Swiss Mathematical Olympiad 2024, second round, task N1. Why N? Because N stands for number theory. So the task is to determine all triplets A, B, and N of positive integers where A divides N, B divides N, and A plus 1 times B plus 1 equals N. So what does it mean? N is divisible by A, so we can write that N equals AK and N equals BM. So let us rewrite the following sentence in this way. A plus 1 times B plus 1 equals AK. Aha! What do we have? We have the product on the left hand side and the product on the right hand side of the equation. So the left part, the right part, right hand side is divisible by A. So the left hand side should also be divisible by A. But what do we see? It has a factor of A plus 1. And the numbers A plus 1 and A, their GCF, greatest common factor of A plus 1 and A, equals 1. So they are co-prime or mutually prime numbers. So A has some factors, but none of them can we find in A plus 1. Therefore, it leaves us no other options but to write that B plus 1 is divisible by A. So since we can, this task is symmetrical to the substitutions of A by B and of B by A, and we can write therefore that not only B plus 1 is divisible by A, but also A plus 1 is divisible by B. This symmetry, my friends, is very useful for this kind of task. If you see the symmetry in the condition of the problem, then there should be symmetry in the solution, and you can use it throughout the entire solution. So what does it mean? If B plus 1 is divisible by A, then B plus 1 should definitely not be smaller than A. Actually, B plus 1 is greater or equal than A, and similarly A plus 1 is greater or equal than B. Aha. So these two inequalities simultaneously tell us that A and B should not really be that different. They're somewhere close because B shouldn't be much greater than A and A shouldn't be much greater than B. So let's prove it more rigorously. Since we have that, let's rewrite the second expression. We have A greater or equal than B minus 1. So, and then we can write the chain inequality. So we just rewrote and then we substitute the second expression for A. Aha! So what do we have? We have A is between B plus 1 and B minus 1. So the possible values of A of B are the following: B plus 1, B, B minus 1. Okay, so there are only three options. And similarly, A of B is the same as B of A because of this symmetry. Symmetry is beautiful. Right. So B is the same. A plus 1, A, and A minus 1. Aha. So what do we have? When A equals B plus 1, B equals A minus 1. They kind of go crisscross. And when A is B, B is A, obviously. And yes, and the last option, when A is B minus 1, B is A plus 1. Aha. So let us consider them. The first and obvious option that we have is when A equals B. So let us consider, and the second option, I'll write it here, that when A is not equal to B. And here, because of the symmetry I told you about many times, we can assume without loss of generality, it means whatever, that A is greater than B. And according to all this statement, actually A is equal to B plus 1. So let us go to the first part, and then we'll find all the possible triplets here, and then we'll go to the second part. So from the first part, A equals B, so we rewrite this inequality as A plus 1 squared equals, what did we write? N is as AK. So then we open the brackets and rearrange the equality. So RA, factorize it, we have 2 minus K plus 1 equals 0. Right, so we have the expression, the discriminant of this quadratic equation is this term squared, 2 minus k. I'll just rewrite it as k minus 2 squared because we nevertheless square it, minus 4. And we know that a1, 2 should be minus b, so it is k minus 2 plus or minus square root of discriminant over 2. And we know a is a positive integer or natural number, k is a positive integer, denominator is also a positive integer, so the square root of discriminant cannot be anything other than the positive integer. And thus discriminant itself should be the completed square of some number. So and what do we see? That k minus 2 squared, it's already square of some number, and d should be square of another number. So the two squares are different only by 4. And let us consider when it is possible. So the squares, square of 0 is 0, square of 1 is 1, square of 2 is 4, square of 3 is 9, square of 4 is 16, 25, and so on. And look at the difference between the squares. It starts to grow as we go further and further. This difference is 7, the next difference is 9. And the only difference we can find of 4 is between 0 and 4. Only this one is 4. All the rest, between 1 and 4 is 3, between 4 is 9, is 5. It is not good. And 7, 9, and then we'll have even greater differences. So only this one can work. And so the discriminant thus should equal to 0, and this k minus 2 squared should equal to 4. Again, because we have found them here, 0 and 4. So then k, according to this, so k should equal to 0, or k should equal to 4. K equals 0 obviously doesn't work because a plus 1 squared cannot be equal to a times 0. So right hand side is going to be 0. It doesn't work. No. No. No, no, no. When you write no, you have to write it accurately. No. Then k equals 4. So 4. So let's plug this number. It returns the 0 discriminant, and thus a equals k minus 2, 2 over 2, a equals 1. Okay, so then let us check. Then b equals 1 also. Then let us check. N equals ak equals 1 times 4 equals 4. So we have a triplet candidate, and let us check. A equals 1, 1 plus 1 equals 2, b plus 1, 1 plus 1 equals 2, 2 times 2 equals, you know it, equals 4. So 4 we divide, and 4 is divisible by a, which is 1, and 4 is divisible by b, which is 1. And so we have a triplet, 1, 1, and 4. And this is the only triplet which works for the case of a equals b. So then let's consider the other case when a is not equal to b, and without loss of generality, I remind you, a is greater than b. So a then is equal to, according to this, to b plus 1, and so we rewrite it as b plus 1 plus 1 plus 2 equals b plus 1, and this gives us, since we're talking about b, let us write it equals bm. So open the brackets, simplify, b squared plus b, what is it, 1 plus 2, 3b, 3 minus m plus 2 equals 0. Fine. Fine. Again, the discriminant we write as m minus 3 squared minus 8. And again, look, the difference between two squares is 8. When it is possible, if and only if we are here, it is between one square is 9 and the other square is 1. I remember both the discriminant should be a perfect square, and minus m minus 3 squared is a perfect square, and 8 is difference between two perfect squares. So the discriminant should equal 1, and m minus 3 squared should equal 9, which is possible for two options, when m equals 6 and m equals 0. Again, m equals 0 doesn't work because right hand side of the equation is going to be 0. So no. Look, I'm getting better at writing no. Some progress also for me. Then we have, let's rewrite this equation, b squared minus 3b plus 2 equals 0. Then we have, it gives us following roots, b equals 1 and b equals 2. Both of them work. Then it automatically returns us a is b plus 1, so it is a equals 2 and a equals 3. And let us plug them. A plus 1, it is 3 times b plus 1, 2. 3 times 2 gives us n equal 6. And then the second option, 3 plus 1 is 4, times 2 plus 1 is 3, 4 times 3 is 12. And let us check. 6 is divisible by 1 and by 2, yes, and 12 is divisible by 2 and by 3. So let us write our triplets. We start with A, it gives us 2, 1, 6, and the other one is 3, 2, 12. And of course, since I told you about symmetry between A and B, the permutations also work. We can rearrange as 1, 2, 6 and 2, 3, 12. So, and this is the complete list of all the triplets. This one, 1, 1, 4, when A equals B, and this 4 when A is without loss of generality greater than B. So 5 triplets. And this is it.